Hello everyone. In this lecture, I shall discuss the complex numbers. Okay. Basically, I will discuss here the preliminaries, the conjugate, modulus of complex number, and the basic properties, algebra of complex numbers, so on. Now coming to the formal definition of a complex number Z, right, or Z is also called a complex variable, is of the form Z is equal to x plus iy. So what is x? X is basically a real number. Y is basically a real number. So I write x and y are the real numbers. And what about your I? I is your minus 1 root over, or I square is equal to minus 1. Okay. So now coming to this complex number Z, here what is the real part of this complex number? This x is called the real part of the complex number, right? This x is called the real part of the complex number, and this y is called the imaginary part of the complex number. However, this I, right, this I is merely a symbol, right? This I is minus 1 root over. Here basically it merely a symbol. It denotes the imaginary unit, right? Imaginary unit. Like your 1 denotes the unit of the real number, unity of the real number, right? Likewise, this I is interpreted here as the imaginary units, right? It is not correct to say that x plus iy is a imaginary number. Rather, iy is purely imaginary. When iy is purely imaginary, when your x is equal to 0, right? Similarly, when y is equal to 0, z is purely real, right? A complex number z is purely real if the imaginary part is 0, and the complex number z is purely imaginary if real part of z is equal to 0, is not it? If real part of z is equal to 0, and it is purely real if imaginary z is equal to 0, right? Is not it? So now for writing z plus iy, this plus here is not actually the addition. It is not actually the addition, right? However, z plus iy means that x real units, right? X is real and y is also real. X real units are superimposed in order, right, by y imaginary units, to produce an ordered pair. So the complex number z is equal to x plus iy with a controversy that x is a real number, y is a real number, and I is not a number. How it is multiplied? So this complex number can be expressed as the ordered pair of the real numbers, right? Ordered pair of the real numbers x, y, and it is equivalent to say x plus iy, where x and y are the real numbers and I is the ordered pair 0, 1, right? It is the ordered pair 0, 1. It is simply a point on the imaginary axis, right? It is the ordered pair 0, 1. I is the ordered pair 0, 1, right? Such that what is your I square? Your I square is equal to minus 1, or I is equal to root over of minus 1. Okay. So with this in view, so that means the complex number can be viewed as a point in the plane, right? Whereas the real number can be viewed as a point on the real line. So now in the sense of this your ordered pair, we write z is equal to x plus iy. So where x is a point real number means it is a point on the real line, so it is x0, and I is my point 0, 1, and y is also a real number, so y0. So now if I multiply it, right, so prior to that let you see, suppose you have two complex number, z1 is a complex number and z2 is a complex number, then what is z1 plus z2 means the real part is added with the real part, means it is your a plus c, and the imaginary part is added with the imaginary part. It is your b plus d. It is your b plus d, right? B plus d. So real part is added with real part and imaginary part is added with imaginary part. If you have a negative sign, suppose I want to subtract it also, likewise we have here real part is subtracted and imaginary part is subtracted here, right? Likewise, what about your product? So we have to always separate it, the real part and imaginary part. If I multiply A into A, then it is real, there is no I here. It is A into C, then there is no I here. You see, A into C, there is no I here, right? So it is SC. If we multiply B into D, so means IB and IB, I square BD is minus BD, so it is my minus BD. So now it is my real part. And what happens to my terms involving I? If I multiply A with D, A is free from I, D is with I, so we have AD involve I, so here it is here AD. Then if B is multiplied with C, B involve I, C doesn't have I, so here BC, it is here BC, AD plus BC, right? So C doesn't involve your I here, BC, so it is AD minus BC, it is the multiplication, right? Multiplication, and it is your addition, So now in view of that, if I multiply it here, okay, I will able to write it. It is x0 plus, you see, it is here 0 into y, right? 0, and if you multiply this with this, it is minus 1, right? Then you multiply 0 with 0 and here 1 with y. So you see the multiplication here it is 0 into, so as per this multiplication here, here it is 0 into y, and here it is minus of 1 into 0, likewise this comma, then here 0 into 0, right? 0 into 0 plus 1 into y. So what will be your addition? So your addition here will be x0 plus, it is 0 y, so this is equal to xy. So you see, right, this complex number z is equal to x plus iy can be viewed as the ordered pair of xy, and here it is viewed as x0 plus I into y0. So this I, even if it is a imaginary number, it is multiplied with your y in the other geometry, means in the sense that it is a point in the plane. It is in the sense of the multiplication of the ordered pair, right? So this is a new aspect here. Now before the details of discussion, let me to introduce myself, Professor Sushant Kumar Paikray, currently working as a Professor of Mathematics at B. Surendra Sai University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss some standard remarks in view of the background of the complex number. I can say here, real number is the geometry of a line, whereas complex number is a point in the plane. That means I can say this is my real line. If I want to denote, it is my 0. If I want to denote, it is my half. If I want to denote, it is my 1, so on. But the moment I represent a complex number, how I will represent it? So it is my real axis x, it is my real axis, and it is my imaginary axis y, it is my imaginary axis, right? By saying xy, I have a I have a point x here, right? This is my x and this is my y. So this point is here z is equal to xy. So complex number is just a point in the plane. It is a point in the plane. Otherwise real number is simply a point on the real line. Okay, point on the real line, right? So now if I say I, so I is simply this point. This is my 0, 1 point. So this I is simply my 0, 1 point. So this is what the geometry of the complex number can be viewed as a point in the plane, right? So now coming to your second remark, if we think of the equality of two complex number, suppose here z1 is a complex number a plus ib and z2 is a complex number c plus id. The moment I write z1 is equal to z2 means your real part has to be same as real part, imaginary part has to be same as the imaginary part. Here real z1 is equal to real z2 and imaginary z1 is equal to imaginary z2, right? If real and imaginary part are equal, then only equal. So that means here we can say a is equal to c and b is equal to d. Okay, so that is this. So coming to the third property, I can say complex numbers are not comparable, right? Complex numbers are not comparable, right? If I say z1 and z2, right? So this greater than, this will not work. This less than, this will also not work. Okay, so if I ask you 2i and 5pi, if I say is it greater than, then your answer is no, it is wrong, right? The answer is no, because it cannot be comparable. So because complex numbers are not comparable because of the imaginary unit I, it is because of the imaginary unit I, right? Similarly, if I say 2i is smaller than 7i, it is also wrong, right? Because these are not comparable. Okay, but however equality can be made by comparing real part same as real and imaginary same as the imaginary. However, if I say suppose 2i mod and 7i mod, okay, I can say it is small because this is converted to 2 now, this is converted to 7. So this inequality will work while I take the modulus, okay, right? Otherwise it will not work. Next, coming to the fourth remark, you have if I ask you root a into root b, right? You can write it root over of ab. However, if I ask you minus of a root over into minus of b root over, right? And you can write it, it is minus a into minus 1. You can write it a into minus 1 root over into b into minus 1 root over. So now here, so this a and b you can write it root over of a into b, and here you write it minus 1 root over into minus 1 root over, right? So you can write it root over of ab into it is minus 1 root over square. So this is equal to a minus 1 root over is I, so minus root, it is your ab into I square, into your I square. So you will write it minus of root over of ab. So you see it, okay? So in view of this, if I say minus 1, now if I write minus 1 root over square, I will able to write it minus 1 root over into minus 1 root over, right? And this is my minus 1 is equal to this. It is my minus 1 is equal to this, or it is my I square is equal to this, right? So now there is a paradox. If I write minus 1 modulus ra square is minus 1 root over into minus 1 root over. If in view of this, if I write minus 1 into minus 1 root over, then it is 1 root over is 1. Then what will happen? This is your minus 1. This is your minus 1 and this is your 1. Minus 1 is equal to 1 is a paradox. That means this thing is wrong here. Okay, this thing is wrong here. Now we can say this C as the set of complex numbers. That means I can write it, my C is equal to Z such that Z is equal to X plus IY, X in R, Y in R. This is the set of complex number. The moment I say what is your C star is your C minus 0, right? Means non-zero complex number. Set of non-zero complex number, right? Non-zero complex number. Clear? Now if I think of the reciprocal, for Z in C star, what is my 1 by Z, right? So let if I say Z is my A plus IB, so then my 1 by Z is 1 by A plus IB. So I should write it that A minus IB is multiplied here. It is A plus IB into A minus IB. Okay, you can multiply it. So it is A minus IB by your A square minus B square formula. It is A square plus B square. So this is A by A square plus B square minus I times B by A square plus B square. Okay, or I can write it plus I times your minus B by this. So in that way we will write. So this is my real part, 1 by Z, and this is my imaginary part of 1 by Z. Okay, so always try to write the complex number in the form of real part plus imaginary part, I times imaginary part. Seventh property I can write Z1 plus Z2 plus Z3 is same as Z1 plus Z2 plus Z3. Means here associative. It is your associative property. Accordingly you have Z1 plus Z2 is same thing as Z2 plus Z1. It is also commutative. This property is your commutative property. And accordingly you have 1 plus I0 is the unit element, is the identity element, multiplicative identity. Is the multiplicative identity. Okay, multiplicative identity. That means if I write Z1 into 1 plus I0, it is my simply Z1 into 1 is my Z1. Likewise I can write Z1 into Z2 into Z3 here. Okay, so this is equal to Z1 into Z2 into Z3. Similarly my Z1 into Z2 is same thing as Z2 into Z1. So here this is my associative property with respect to multiplication, and this is my commutative property, right? This is my commutative property with respect to multiplication. Coming to property number 8. Remark 8, if I write alpha into Z1, so that is equal to my alpha into Z1 is suppose my A plus IB, right? I can write it alpha A plus alpha B I. Now coming to the algebra of complex numbers, your addition Z1 plus Z2 is equal to your A plus IB plus C plus ID, means your real part is added with real part, imaginary part is added with imaginary part. It is a plus c. This is a plus c plus I times b plus d. Okay, or we can write it in order pair form, a plus c b plus d. Then coming to your multiplication, z1 into z2, it is a plus ib into c plus id. So that is equal to your ac minus bd plus I times your AD plus BC, AD plus BC. So in ordered pair form, it is AC minus BD, comma AD plus BC. Similarly, for your division, your Z1 by Z2 is equal to, you will write A plus IB into 1 by C plus ID. Okay, so you should split it in that way. Write the reciprocal of the complex number 1 by Z. In that way you have to split, right? And you will write it A plus IB into C minus ID divided by C plus ID into C minus ID. Okay, so now in the denominator it is C square plus D square. So in the numerator it will be AC plus BD, AC plus BD, right? AC plus BD, comma, and it is here BC minus AD, BC minus AD. So you will able to write it AC plus BD by C square plus D square plus imaginary part is I times BC minus AD by C square plus D square. So it is of the form P plus IQ. So always try to write the complex number in the simplified form. This, suppose I ask you that proof I square is equal to minus 1. How to prove it? So I square is I into I. So this is equal to here I is the 0 1 and into 0 1, and it is the multiplication of the complex number. So it is 0 into 0, right? Minus 1 into 1, minus 1 into 1, comma, it is 0 into 1 plus 1 into 0. So you will write it, it is minus 1 0. Just 1 second. Yes, so it is here minus 1. So therefore your I square is equal to minus 1. Okay, so I square is equal to minus 1 is proved, right? This is your minus 1, right? So this is proved.
Argonne diagram. Argonne diagram.
Argand.
Argand,
Argand.
Argand,
Argand. Thanks for watching. Please subscribe to our video. Argand.
Argand. Argand. Now let us see the geometric representation of complex number. As you know, here z is equal to x plus iy, right? It is in Cartesian form. Cartesian form. Now if I put it, x is equal to r cos theta, y is equal to r sin theta, and your Euler's formula e to the power I theta is cos theta plus I sin theta, then you will able to write it. Here z is equal to r into e to the power I theta. Okay, it is in Gaussian form. So here z is equal to x plus iy is the Cartesian form. Also this is the Gaussian form. But this I, okay, but this I is equal to minus 1 root over. This I is equal to minus 1 root over is meaningless. In real number, and it was introduced by Euler. This I is equal to minus 1 root over was introduced by Euler. Okay, now this formula is the Euler's formula. So in view of this, so z is equal to this is known as the polar form or Eulerian form. So we will discuss in next lecture. We will discuss in details. In next lecture I will discuss about this amplitude or argument of z, right? Argument of z my theta. In next lecture I will discuss it. So now coming to this geometrical interpretation, every complex number can be represented by a point in the organ plane. So geometrically every complex number can be represented by a point in the organ plane. So that means the plane is, so this is the xy plane here. This is the real axis. This is your imaginary axis here, and this is the point here. Okay, and this point, if this is my x and this is my y, then this is my z is equal to x plus iy, right? This is your z is equal to x plus iy or x y ordered pair. Okay, this is called the organ plane. So every complex number can be represented by a point in the organ plane. Okay, so now if you think of this rotation here, right? This angle is theta here, in anticlockwise sense. Then this value and this distance here is z mod, or this will be your r. Okay, this will be your r, right? And this r will be your root over of x square plus y square. It is called the modulus of z. In next lecture I will discuss the details about it. So now just one point I will say. So I can say here, if z is a complex number, then iz is obtained just by rotating z through a right angle without changing its length. Means you see, what is your z? Z is equal to r cos theta plus I sin theta, right? And likewise you can write I is equal to cos pi by 2 plus I sin pi by 2, because cos pi by 2 is your what? 0, sin pi by 2 is your 1, right? Now what happens to your iz? So iz is cos pi by 2 plus I sin pi by 2. It is multiplied with r cos theta plus I sin theta. You know IR sin theta, you can write it. So now you multiply it. You know the multiplication of two complex number. If you multiply it, we will find it r cos theta plus pi by 2 plus I sin theta plus pi by 2. So what we conclude? So here we have the rotation was theta, but here we are getting here theta plus pi by 2. That means if we have this is my x, if this is my x, right, and this is my rotated and at an angle theta here, and I am getting it, suppose my z I am getting, z is equal to, suppose I am getting z is equal to x plus iy here, means r cos theta plus I sin theta. So now it is theta. So this theta plus pi by 2 means now this is now making the 90 degree here. Okay, this is making the 90 degree here. So it is theta plus pi by 2, and I will get this is my iz. Okay, so this iz is obtained by rotating z through the right angle without changing its length, right? Now coming to the conjugate of z, if your z is equal to x plus iy, then what happens to your z conjugate? Your z conjugate is x minus iy. That means what happened here? Means here y is replaced by minus y, right? Y is replaced by minus y. So likewise, if I ask suppose z is equal to minus a minus ib, what happens to your z conjugate? It is minus a minus of I into minus b. So this is minus a plus ib, means that the imaginary unit here is replaced by minus 1 times the imaginary unit. Okay, so geometrically if you think of its representation, if this is my x and this is my y and this is my z, okay, this is my z is xy, then it is my z conjugate will be here, z conjugate will be my here, right, z conjugate. So here my z conjugate will be x minus x comma minus y. So that means geometrically you see this is simply the reflection of this. If this is in clockwise anti-clockwise sense, this is theta, and this will be in anti-clockwise sense, and it is negative minus of theta. Okay, so now geometrically you can write z conjugate is the mirror image or reflection of z. So that means I can say geometrically z conjugate is simply the reflection or image of z about x-axis, or I can say z and z conjugate situated symmetrically about x-axis, right? Now coming to the properties of this z conjugate, properties of conjugate. If I have z1 is equal to a plus ib, and z implies what will happen is z is my a plus ib, then what is your z conjugate? So z conjugate is your a minus ib. So if you add them, z plus z conjugate, then it is twice a only. That means a is your real part of z. If I subtract them, right, then here this a cancelled, it is 2ib, right? So b is my imaginary part of z, so this is 2I imaginary part of z. So we can have the properties of the conjugate. I can write z plus z conjugate is twice real z, z minus z conjugate is 2I imaginary z, or I can write z minus z conjugate by 2I is my imaginary z. I can write z1 plus z2 conjugate is z1 conjugate plus z2 conjugate. Similarly for minus. Now it will not work for here, minus, okay? And similarly here z1 into z2 conjugate is individually z1 conjugate into z2 conjugate, and similarly here z1 by z2 whole conjugate is z1 conjugate by z2 conjugate, and provided your z2 is not equal to 0. Okay, coming to third property, z conjugate whole conjugate is equal to your z. Now coming to the fourth property, if z is real, then here z conjugate is same thing as z, because I have told you x plus iy conjugate, then here y is replaced by minus y, right? If I write suppose 5 conjugate, so there is no imaginary part, it is same as here 5, okay? So z conjugate is equal to here z. So these are the properties of the conjugate. So here z conjugate, it reads as conjugate of z, or z conjugate, okay? Now coming to the modulus. Now if z is equal to x plus iy, okay, the modulus or absolute value of z is given by modulus of z is x whole square plus y square root over positive square root of. Means I mean to say here is that if we have a complex number here, we have this is my x, and this is my y. So now this is my z, and this distance is my here z mod is x square plus y square root over, right? So this distance is my x square plus y square root over. So this is my x and this is my y, and this will be my x square plus y square root over. It is modulus of z, right? So now it is immaterial. So we have z may be anywhere, z may be here in the first quadrant, or z may be here, or z may be here, or z may be here. It is x plus iy, it is minus x plus iy, it is minus x minus iy, it is x minus iy. So if I take this distance, any distance I will take, and all these distance are same, okay? All these distance are same, right? All these distance are same, right? So if I take z is equal to minus x minus iy, what is z mod? It is minus x square plus minus y square root over. This is here x square plus y square root over. So this is my modulus of z. So modulus of z indicates the distance from origin to z. Now coming to some standard properties of modulus, we can say z mod is always greater than is equal to 0, because it is the sense of the distance. And here z mod is equal to 0. What does it mean? If and only if here z is equal to 0, right? Coming to property number 2, z into z mod is z modulus square, okay? And this is also z square modulus. You can prove it. Suppose z into z modulus is suppose a plus ib into a minus ib. So this is equal to a square plus b square root over, right? Is it not your z modulus square? Similarly, if I think of z square is equal to here x plus iy square. So this is equal to x square minus y square plus I 2xy. Now if I take z square modulus, it is x square minus y square whole square plus 4x square y square. So this is here x square plus y square whole square, right? A minus b whole square plus 4ab is a plus b whole square, okay? So that is my, this modulus is root over of this. So this is here x square plus y square root over is here z modulus square, okay? So therefore z into z conjugate is z mod square is z square mod, okay? Likewise I can write it here zn mod is the same thing as z mod to the power n, okay? Then coming to your next property number 3, here z1 into z2 mod is z1 mod into z2 mod. z1 by z2 mod is z1 mod divided by z2 mod, and where z2 is not equal to here 0, right? Coming to the fourth property, z1 plus z2 modulus square is equal to z1 modulus square plus z2 modulus square plus twice real z1 z2 conjugate. And property number 5th, z1 minus z2 modulus square is z1 modulus square plus z2 modulus square minus twice real z1 z2 conjugate, okay? Then coming to property number 6, z1 plus z2 modulus square plus z1 minus z2 modulus square is twice z1 modulus square plus z2 modulus square. This last equality is called the parallelogram equality. Parallelogram equality. Now coming to some inequalities, important inequalities. So coming to some standard inequalities, we can have real z is less than equal to modulus of z, and imaginary z is also less than is equal to your modulus of z. Now property number 2 is important. z1 plus z2 mod is less than is equal to z1 mod plus z2 mod. It is a triangle inequality. Okay, triangle inequality. In view of this, we can have the third property. Here z1 minus z2 mod is greater than is equal to z1 mod minus z2 mod whole mod. So let us prove this. Coming to proof of 1. Okay, what is here? Z is equal to suppose x plus iy. So what is your real z? Real z is x. Your imaginary z is what? Y. So here modulus of z is what? X square plus y square root over. You see here whether x is less than is equal to x square plus y square root over, yes or no? For y is greater than equal to 0. So that's why here real z is less than equal to your mod z. Likewise we can write y is less than is equal to x square plus y square root over for some y, right? Some y may be greater than equal to 0, or if y is not greater than equal to 0, then also we are taking whole square. So now this is your imaginary z here, right, is less than is equal to, this is your modulus of z. Now coming to proof 3. Proof 3, the triangle inequality is important. Now coming to z1 plus z2 mod square. You know z1 plus z2 into z1 plus z2 conjugate, because you know z conjugate is z mod square. So now you can write it now you can write z1 plus z2, and this is z1 conjugate plus z2 conjugate, properties of the conjugate. So now you multiply it, z1 conjugate, okay, plus z1 z2 conjugate plus z2 z1 conjugate plus z2 z2 conjugate, okay. So now you can write it, this is here z1 modulus square, and you can write it z1 z2 conjugate plus z1 z2 conjugate whole conjugate. Then there will be conjugate on z1, no conjugate on z2, plus this is your z2 modulus square. So now you will be able to write it, this is z plus z conjugate is twice real z. So this you will be right z1 modulus square plus twice real z1 z2 conjugate plus z2 modulus square, since z plus z conjugate is twice real z, okay. So now you will able to write it z1 modulus square, and you know real z is less than mod z, so you can write it here, modulus of less than equal to sign, because twice z1 z2 conjugate mod plus here z2 modulus square, since you know real z is less than equal to mod z, okay, right. So now you split it, so this is equal to your z1 modulus square plus z1 into z2 mod is z1 mod into z2 mod, z2 conjugate mod plus z2 modulus square. So now this is same thing as z1 modulus square plus twice z1 mod into z2 mod plus z2 modulus square. The reason is z conjugate mod is same thing as z mod, okay. So now you see what we are getting, this is z1 mod plus this is z2 mod whole square, is not it? So you see, if you compare this, we have a in less than equal sign. So therefore what we are getting, z1 plus z2 modulus square is less than is equal to z1 mod plus z2 mod whole square. Now taking the square root to both sides, what we are getting, z1 plus z2 mod is less than is equal to z1 mod plus z2 mod. So it is proved, okay. Likewise you will able to prove the next one. So this will also work, z1 minus z2 conjugate also it will work here. Both for plus and minus it will work. Okay, so in view of this we can prove it. So this is z1 minus z2, z1 conjugate minus z2 conjugate individually. So that is equal to, if I multiply it, now in view of this previous one, here there will be just a negative sign here. Now the moment I write z1 modulus square minus twice modulus of z1 z2 conjugate plus z2 modulus square, you see this is a large quantity. This is large. Yes or no? Large is subtracted. So here this is small. The smaller one is subtracted, right? So definitely this part will be greater than this. So I can write it greater than equal to, right? So here I can write it now. So in the same manner, so this is my z1 mod minus z2 mod whole square. So can I not write the same thing as z1 mod minus z2 mod whole mod square, because this is a positive quantity and this is also positive quantity. So what I am getting here? So I am getting here z1 minus z2 modulus square. Now if I take the square root to both sides, what I am getting? z1 minus z2 mod this is greater than equal to, because this greater than is persists here, is greater than equal to z1 mod minus z2 mod whole mod. So this is proved. Okay, coming to some examples. So likewise we can have some properties. I can say z1 plus z2 plus zn mod, and it is z1 mod plus z2 mod, so on plus zn mod. Likewise also z1 z2 zn mod, if I multiplied it, z1 mod into z2 mod here zn mod. Okay, now coming to some solved examples. Now coming to the question, verify this is I and this is minus I. Also find the modulus and conjugates, moduli in plural and conjugates. Okay, so now 1, here z is equal to 1 plus I by 1 minus I. We have to rationalize it, make it free. So this is here 1 plus I into 1 plus I divided by 1 minus I into 1 plus I. I multiply its conjugate in the denominator. So this is 1 plus I square by, it is 1 square plus 1 square root over, it is 1 square plus 1 square, because here z into z conjugate is z mod square. Okay, so in the numerator you have a plus b whole square 1, I square is minus 1 plus 2ab 2i, right, 2i divided by your 2, this cancel, this is your I by I. So therefore what is your z mod? Your z mod is equal to, so this is 2i by 2 cancel, this is your I. So z mod is equal to I mod is equal to your 1, right, because 0 square plus 1 square root over, right, is equal to your 1, right. So now what is your conjugate? Now conjugate of z is equal to conjugate of I. So 0 plus I conjugate, so the imaginary part is just negative, it is minus I, right, minus I. So similarly here coming to your 2, you will get it, z is equal to 1 minus I by z is equal to 1 minus I by 1 plus I. You can make it 1 minus I square by 1 plus I into 1 minus I. So this is equal to 1 minus 1 minus 2i by 2. So this is equal to minus I. So what is your z conjugate here? Z mod here minus I mod is equal to here 1, and what is your z conjugate is minus I conjugate, so it becomes here plus I. So this is your solution answer. So to conclude, through this lecture we have discussed the preliminary things, the modulus and conjugate. Okay, so the basic difference is real number is the geometry of the real line, any point in this line. However, the complex number is a point in the plane. Okay, it is a point in the plane. This is the basic difference here. And this I square is minus 1 is also a point in the plane, minus 1 0. It is in that way it is interpreted. And the inequalities what we prove, the triangle inequality, parallelogram equality, these are most important. So now we should conclude here because the video is getting lengthy. Okay, So if you feel this lecture is interesting and useful, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures. In my upcoming lecture I will discuss the modulus, the amplitude, argument of the complex number, argument of z, the principal argument and the general argument. I will discuss in details, and I will find the nth root of the complex number. I will discuss. Okay, so with this we should close it here. Thank you all for watching. Have a nice day.